let's consider what happens when a mass m changes its altitude by delta y. Now really delta y should be an arrow pointing straight down. I've got it pointing in both directions, and that's a bad habit that I have. But delta y, if it changes from here to here, is going to give us a certain change in kinetic energy. Now, the potential energy that we gain by raising the object from here to here is nothing but its weight times delta y. What's the weight of an object? The weight is the mass times the mass of the object times the acceleration of gravity. So as the object is raised from here to here, the force that we have to exert to raise it at a constant velocity and increase its potential energy is going to be equal and opposite to the mg, that is its mass times 9.8 meters per second squared. It's going to give us the force that we need to exert, and delta y is going to give us the distance through which we have to exert it. So that the work we do is m times the magnitude of acceleration of gravity, 9.8 meters per second squared, times the delta y. And I'm using delta y pretty ambiguously. I talk about delta y going this way and then going this way. In this case, delta y would be going up. That's the work we put into it. Now if that delta w increases the potential energy as it does, and if all that goes into the kinetic energy, and really I should have an arrow, delta w goes to potential energy, goes to kinetic energy here. In any case, if the delta w that we do goes to kinetic energy, then, well, the kinetic energy is 1/2 mv squared, and that's going to be equal to our mg delta y. In that case, we're going to arrive at velocity is the square root of 2g delta y. Okay, now, we have velocity proportional to delta y, to the square root of delta y. That means velocity squared would be 2g delta y, so velocity squared would be proportional to delta y. Remember, the mystery we're trying to solve here is why the delta x squared should be proportional to delta y. Well, that would be the case, of course, if delta x was some constant number times delta y. We note that v is a constant number times delta y. The constant number is just our square root of 2g times the square root of delta y. Then v is constant times the square root of delta y. This implies that delta x is proportional to v, because delta x is proportional to delta y and v is proportional to delta y. If we eliminate delta y from these two equations, we find that delta x and delta v are just proportional to each other. One is a constant times the other. Well, when is delta x proportional to the velocity of the object? When the velocity is constant. So it seems that we have evidence that the velocity of the ball coming off of the end of the ramp is constant.